Hi, everybody. Welcome to the phiVis Philosophy of Vision Science workshop. My name is Kevin Landy, and I organize this event along with Chaz Firestone. I am, as of just a few weeks ago, an associate professor of philosophy. Thank you very much, at York University, where I'm also a member of the Center for Vision Research. My work's in the philosophy of vision science, and in this area, philosophers try to answer basic questions about the nature of perception, mind, knowledge, and by thinking deeply about the results and paradigms of vision science. 4.5 years ago, I thought it would be good to get more philosophers to VSS, despite the fact that I'd never myself been to the conference. I heard about this magical beach conference that was the beating heart of vision science. And as someone who spends as much time reading vision science as I do philosophy, I knew that I and other philosophers had to make the pilgrimage. At the same time, I was realizing that a lot of scientists that I was meeting really like talking to philosophers. On the clock, there's no time for philosophizing. Off the clock, they would take every chance to talk about the mind-body problem, the nature of reality, the possibility of knowledge, or what makes something truly a sandwich. So I decided to reach out to people that I knew in both philosophy and science and get their opinions on how we might get philosophers to VSS. And Chaz, more than anyone, was all in. He said he was going to make this happen however we could. So we became partners in this. We talked to Laurie Wilcox, then the president of VSS, and we settled on an idea of a satellite event. We gave it a name that we thought that everybody can agree is easy to remember and easy to pronounce. phiVis. And that was the year that VSS went online. But as it happened, we got the word out. Well, Chaz really got the word out to his legion of Twitter followers. We had over 300 people attend the event online, and we were blown away by the response. And the emails that we received afterwards, describing the hope and excitement that the event inspired. We were nervous about whether the momentum would stick when we went in person, and yet each time we did it in progressively larger rooms, it was at capacity. People were sitting on the floor. We did eventually find a chair for Jeremy Wolf. The support we've seen on social media and in emails has been super encouraging. People have skipped kayaking trips to watch philosophers give talks in a windowless room. And it's rewarding to see that the event is now having some small part in new and exciting work coming in both philosophy and psychology. None of that's to say that communication across fields is always smooth. We're often driven by slightly different questions and concepts and priorities, and it can take a lot of work before we feel like we're on the same page. So the goal of phiVis is to get us on the same page and find places where the conversation can be illuminating and even just fun. None of this would have been possible without our sponsors at York University, the Philosophy Department, the Center for Vision Research, the Vision Science to Applications Program, at Johns Hopkins University, the William H. Miller III Department of Philosophy, and the Vision Sciences Group. I'll hand it over now to Chaz to say a few things, and then we'll get things started.
Thank you, Kevin. My name is Chaz Firestone, and I'm an associate professor of psychological and brain sciences at Johns Hopkins. But I also have a courtesy appointment in the William H. Miller III Department of Philosophy. We got a gift. It was like a huge gift, but now our department has a new name. And in fact, several members of my lab, including some alumni who are even here, have degrees in philosophy and work at the intersections of these two fields. I remember Kevin's initial email very well because it arrived at a very exciting time in my life. Here's how I wrote back. It arrived the same day that my oldest child, Zeke, was born. And so I actually now have like a really convenient way to remember the age of phiVis. It's the exact same age to the day as my child, Zeke. Zeke actually has a younger brother now. And so that might mean that like a phiVis book is on the way or something. I'm not totally sure. Now, having one foot in the door of philosophy has really helped me appreciate the care and attention to detail that philosophers bring to their engagement with the empirical literature. They basically cultivate deep, careful thinking as their intellectual superpower in ways that I know our field can benefit from because I know how much our own lab's work has benefited from it. But like Kevin says, our disciplines differ in various ways. We often don't have quite the same language or background. And so part of our goal with this workshop is not only to actually have interdisciplinary conversations between philosophers and vision scientists, but also to sort of like practice having them better. And there's really no better place for this than the center of the vision science universe, which of course is VSS. So let's get to it. I'm going to turn things back over to Kevin, who will tell you about our schedule.
So we're going to have 3 20-minute talks from philosophers of vision, and each will be followed by a brief discussion from the vision scientist. And after each round of comments, we'll have time for just a question or two. We have a mic on a podium up here if you want to line up for questions. And we're going to start with Gabe Greenberg, Associate Professor in the Department of Philosophy at UCLA. Once I switch over to this thing. Take it away.
Thank you so much for coming, and thank you to the organizers. I am so happy to be at a conference where I can wear shorts. Do I have to actually talk into the mic?
Yeah.
Or can I carry it?
Oh, wait, we can give you a handheld mic. Wait.
Okay, that would be great. Okay, while we're doing that, if you're the kind of person who likes, thank you so much, to see your PDFs, you can use this QR code to get them online. Take a photo, you'll get it. If anyone wants that in a moment. I'll bring it out for the links. Okay. So the topic of today's talk is neural images, and I want to be exploring the question of the format of representation. Sorry, of the format of representations that are in retina topic areas. And I want to begin investigating this question by asking the question: what's the computational function of retinotopy? It's commonly thought that retinotopy is the result of functional constraints and wiring optimization. And this kind of perspective has given us explanations of a variety of kinds of neural morphology, like orientation maps in V1, or the differentiation of different visual areas across the cortex. But in the sense that all brain regions are the result of function plus wiring optimization. So we want to know what kind of function specifically drives retinotopy. That's the question I want to ask today. And here I want to consider two broad kind of hypotheses. They're not mutually exclusive, but they kind of occupy different ends of a spectrum. On one, you think retinotopy is explained in a retina-based way, that the organization of the retinotopic layout of D1, for example, is a product of the organization of inputs coming from the retina. And another kind of explanation, I'll call computation-based explanation, says that the organization of V1 derives from the kinds of computations that it feeds into and facilitates. You might think of this as, like from a design perspective, is retinotopy something that you merely have to tolerate in your machine versus something you actually try to cultivate to facilitate certain kinds of computations? So I'm going to be pursuing a hypothesis, providing some evidence for a hypothesis that's in the second class, kind of computational style explanation. And I want to propose that retinotopic representations are picture-like representations, and that these picture-like representations are a kind of necessary precursor to reliable convolutional computation. There have been parallel arguments in the literature kind of aiming for the same conclusion, that retinotopic maps are some way iconic or picture-like. And they just have kind of taken different routes there. So I take these to be convergent arguments. And the conclusion classes retinotopic maps with other kinds of what philosophers tend to call iconic representations in psychology, such as allegedly mental imagery, iconic memory, the atomic buffer, analog magnitude representations, possibly place codes and rate codes in addition. So I have something specific in mind by the claim that retinotopic representations are picture-like. And I mean, first of all, that they have a 2D, they form a 2D surface. And second of all, that 2D surface is related to or encodes 3D space via some kind of perspective projection. Perspective projection is just sort of a family of methods for mapping 3D space to 2D space via a viewpoint or a station point. If retinotopic maps are picture-like in a sense, that means that they they have the 2D cortical space functions as a kind of, or putting quotes, a place code of some kind, or space code for locations in 3D visual space. And so you can see in this little diagram, the picture would be that locations in the 2D surface of V1 would actually encode via a process of projection locations in the 3D environment. So if you notice, the definition of picture likeness has sort of these two components. One is the intrinsic dimensionality of the surface, 2D surface, and the other is its relationship to the environment. And I'm going to proceed through the argument, essentially following those two steps. So the first step of the argument is to provide evidence that retinotopic areas produce functional 2D representations. Here I'm going to introduce a concept of an accessibility metric for functional space. And the second step is to argue that functional 2D representations in the retinotopic areas are genuinely picture-like. And here's where I will draw on this kind of convolutional models of visual process. So we'll start with step one. So there's this problem of what I call the problem of spatial sensitivity, which is that retinotopy is a property of physical space. Neurons that are physically adjacent in the cortex have receptive fields that are adjacent in visual space. But physical relations, this is the problem, generally aren't computationally relevant for brains and for neural networks, where the core computational elements are neurons and the connections between them. And this is what allows us to give these kind of abstractions from neural nets that treat the links as basically unspatialized. Philosopher Ned Block developed this into an objection. He thought, look, retinotopy just can't be functional because for this reason, because space isn't functional for brains. And Coughlin replied that retinotopic areas form what he called functional spaces, neural populations that in some way function as if they were spaces. But what is a functional space? I think, from that literature in the 80s and 90s about mental imagery, we never got a really satisfying answer to that question. And one of the abiding problems is that you can't define a functional space just as a representation that represents space. It's not enough just to have content that is spatial. So I think the hippocampal representations form a nice contrast where they clearly have spatial content, but they're not arranged in any kind of topology the way that retinotopic areas are. They don't invite the at least initial assumption that they form any kind of functional space in the same way. I'm going to have to skip some of these graphics, but feel free to ask about them. So I think we can get some guidance here about what functional space is by looking at the principle of wiring optimization. Again, the thought is that in circuit construction, the brain is going to optimize function and wiring length. This means that all else equal, physical distance between nodes is proportional to the demand for the outputs from those nodes to be compared. So if we have two nodes that have strong functional convergence, we can expect them to be quite close to each other spatially. And if they have a weak functional convergence, we expect them to be farther from each other spatially. That means that by looking at retinotopy, the physical feature, we could infer backwards to some kind of functional topology of informational relations. And that's exactly what I now want to kind of define a more precise notion of a functional space. So let's introduce this idea of an accessibility metric. It's a distance metric, but it measures how informationally accessible one node or neuron is from another one. We think that the accessibility distance between two nodes is proportional to the number of nodes that they both output to. And as a result, a functional space is the space that's defined by a full set of accessibility metrics. So where we have a physical metric for physical space in a purely kind of functional diagram, we can measure accessibility. To give you just a very simple example, here's like a one-dimensional feed-forward network. Think anytime that two nodes feed into the same output node, their distance apart from each other is 1. If two nodes feed into two of the same output nodes, their distance apart from each other is going to be 0. And the result is going to be a very simple kind of functional space. Of course, any collection of neurons can define a functional space. But in kind of large, flat, feed-forward, sparsely connected neural networks, they tend to produce approximately 2D functional spaces. This diagram shows that if you use a kind of 3x3 convolution with a stride of 1 across the feature map, you end up determining a very well-behaved two-dimensional city block measure. Okay, so we've moved from physical retinotopy to some kind of functional retinotopy. The idea that neurons that are nearby one another in functional space have receptive fields that are nearby each other in three-dimensional visual space. From wiring optimization, we could infer from physical retinotopy back to functional retinotopy. And the kind of way to interpret the pictorial hypothesis that I started with is that picture-like representations occupy functional 2D spaces in the cortex. Okay, let's now move to the second stage, which is thinking about the relationship between these 2D representations and the external world. If you think of visual computation in kind of local terms, like you're focused on the relationship between simple cells and complex cells, then there's not much motivation for thinking about the broad 2D geometrical features of the computation. You really need something global that looks at the whole visual field map and takes that as its input and works on that. So we need something that treats like this whole bank of nodes as the representation and this whole bank of nodes as computation. Of course, this is exactly what convolutional models of vision give you, which is a very large scale picture of how layers of visual representation are supposed to feed into computation. What is convolution? Just a very brief reminder. I'm sure it's a very familiar concept in this room, but many definitions. I'm thinking of convolution as an algorithm that takes an input feature map, produces an output feature map, and it does so by applying a single spatially local nonlinear transformation, the kernel, uniformly across the input map. So that's this kernel moving uniformly across the input map. And as it moves across, it generates output values in corresponding locations of an output feature map. A convolutional neural net is just an iterated hierarchical sequence of these convolutional operations. Space plays a critical role in convolution. You could even think of convolution as a kind of spatial algorithm. It's quite clear from the kind of diagram, you can think like it's working on a 2D surface, and the kernel itself is defined in terms of its spatial properties. And specifically, we could focus on the fact that the kernel is local, as in it only looks at local elements within the input feature map. It's spatially uniform, meaning that it doesn't change size or orientation as it slides across the feature map. And it forms something we could call mapping, which is it takes inputs on the input feature map and associates them with values on the output feature map at the quote same location. So there's a kind of location preservation between input and output maps. I think this means that convolution really does rely on the 2D metric of its representations as opposed to just, say, their topological relationships. Okay, now there's these very familiar models of convolutional models of visual processing that have had a variety of achievements at this point. They're actually directly inspired by the architecture of V1 in their original conception. They've now achieved human-level categorization accuracy as well as a variety of other benchmarks. They recreate the size and abstraction hierarchy of the visual pathways. They've been able to predict the contour map organization, and sort of most probably salient in this audience is that activity levels in early, middle, and late stages of convolutional neural nets have been shown to correlate quite strongly with activity levels in early, middle, and late stages of the ventral stream. Of course, these are far from complete models of vision, but their achievements are suggestive. Now, what I want to do is take these models quite literally, think And to take them literally is to think that layer-to-layer computations in the visual pathway are literally convolutional operations. We could think of these in terms of intra-area computations, like the relationship between layer 4 and layer 2-3 and V1 or V2, or we could think of them as inter-area relationships, like the relationship V1 to V2 or V2 to V4. To take these literally, of course, we can't think of convolution as this serial rewrite process that it takes the form of in digital computers. We have to parallelize that process. And so to do that, we just think of a parallel set of nodes as the input feature map, a parallel set of nodes as the output feature map, and the connecting nodes where the motif repeats, the transformational motif repeats for each node as the kernel. So what gets stretched out in time in the digital algorithm gets stretched out in space in the parallel implementation. The kernel itself we could think of as an orientation pinwheel or a hypercolumn, and we could think of the tiling pattern of the kernel as the roughly kind of even mosaic of contour maps across the visual area. Okay, now I want to ask the question, why does convolution work? And another way of putting this is, why is convolution a reliable algorithm for extracting visual features? In general, so just here in the diagram, which I'll be repeating, we've got a kind of illustration of the convolutional algorithm with an input feature map, output feature map. For an algorithm to be reliable, there has to be some environmental regularity that it's tracking. So typical kind of environmental regularity might be noting that when there are certain arrangements of fragments in 3D space, that we can infer a certain arrangement of contours in 3D space. And there also has to be a systematic relationship between the inputs and outputs of the algorithm and the inputs and outputs of the environmental regularity. So to illustrate this, here's our algorithm down here. Here's the environmental regularity that's being trying to be tracked, roughly like contours from fragments. And there has to be some kind of systematic grain world relationships between the maps and the elements of the 3D environment that they're tracking. These grain world relationships are what philosophers call semantics. I know that that's not the way that term is used in this room, but that's a little philosophers for the day. Now, in vision, the environmental regularities, many of the environmental regularities that have to be tracked involve spatially local features in 3D space being related to more global or more complex features at the same location in 3D space. And so the example of inferring fragments from contours is a good example because you think there are fragments at these set of locations and there's a longer contour at the same location. There's a really nice paper by Associate Professor Kevin Landy on this very topic, which I will return to in a moment. So you've got an environmental regularity that involves fragments, small elements in 3D space being related to larger elements in 3D space. And you're computing that using an algorithm that uses elements in the 2 space of one feature map and mapping them to elements in the 2 space of another feature map. We need some systematic relation to relate elements in the 2 space to elements in the 3 space. And it is perspective projection under transformation, which is going to fulfill that role. So the systematic 3D, 2D relations, I think, are provided by perspective projection. So that's handled by optics. That's the relationship between elements in the 3D world as they map to the retina, followed by a kind of smooth transformation, which takes locations in the retina and more or less smoothly maps them onto locations in V1. This is what, again, as a philosopher, we call a projection semantics, because it's a theory of the environmental relations in terms of projection. This idea that you could extend semantics to vision is what Kevin explores in that paper and gives a really nice architecture for how we might pursue this kind of project. So I think of this as dovetailing with the general agenda. Now, I think these kinds of systematic relations embodied by these projection relations is what makes convolution possible. If some kind of feature, like take a feature F that you are trying to, that's represented by your input map, and a feature G that's represented by your output map, like fragments and contours. If the fragments systematically project to the visual field map, then a convolution can reliably extract representations of contours. On the other hand, if the fragments do not systematically project to the visual field map, then convolution cannot reliably extract contours. So to give the good case, here we can see, here's some fragments in 3D space. They're related by projection to locations on a 2D feature map. Then we can think by local analysis, what convolution does, locally moving across this map. We can, in a reliably way, produce outputs which are projections of contours into space. That's a reliable way of producing that algorithm. On the other hand, suppose that the formal projection is non-systematic and elements of the feature map are sort of randomly associated with different locations in 3 space, then no kind of local computation moving across here will give you any kind of reliable computation of contours in 3 space. Yep, let me this is my final one. So to kind of dramatize the point, here we have a picture-like representation of some values in a triangle shape on a feature map. Painstakingly went down and wrote this very same values down in this kind of Cartesian abstraction here. You can note that this data point in blue is the same as that data point there over there. If we ran a 2D kernel over, like a 2x2 kernel over this, we think that would be a quite reliable way of extracting where are the edges and corners in this feature map. But if you ran a 2x2 kernel over this representation, you could see you would just get noise and garbage. You would discover some things about the representation, like all the periods are in a diagonal line, but that has nothing to do with the content being listed. So in summary, I think Renatopy implies the existence of functional 2D visual field maps. If layer-to-layer computations are convolutional, then the 2D visual field maps stand in functional relations of perspective projection to the 3D visual space. And I take this as sort of initial confirmation for or support for the pictorial hypothesis that there are computationally functional picture-like representations in Renatopic areas. Thank you very much.
Thanks. We're going to move to comments from Jennifer Groh, professor of in the Department of Psychology and Neuroscience at Duke University. Once I get your slides up.
Sure. All right. Thank you. Thanks, Gabe, for that really great fun talk. And you're tall, so I'm going to lower this. And you could consider the title, the shorter title for me is Yes and. I want to take you through a couple of additional examples of cases where there's a real interesting interplay between representational format, how something is encoded, and the computational algorithms that are facilitated by that way of encoding information. And to do this, I want to take you, if I succeed in advancing slides, this one, do it there, to an additional sensory domain, namely the auditory system. So one of the challenges we have in sensory processing is to combine information from different sensory systems. So you've just heard some elegant description of how visual information is encoded in retinotopic maps. This is a vision conference, so let me just get oriented a little bit to sort of, a base of knowledge here. How many people think that there's a similar auditory map of the brain? All right. If I exclude data from barn owls, how many people think there's an auditory map of the brain? Okay, so fewer. Good, because I'm going to tell you there isn't, in the mammalian brain at least. What? Yeah, good. So I'm hooked you already. Okay, so the visual and auditory systems use very different ways of detecting spatial information. So for the visual system, of course, there's optics of the eye that ensure that light coming from different locations will hit different places on the retina. So each photoreceptor effectively only sees one place, and what Gabe was just telling you about is how that organization is maintained and what it can help us do. But for the auditory system, there's no such image formation. Okay, sounds coming from different locations in space are going to get funneled down the ear canal. The inner ear is going to hear all places, and the brain has to then compute location from cues in that signal. It does so using, among other things, interaural timing and level differences, which is to say that if the sound is located off to my right, it's going to arrive in the right ear before the left ear, and it's going to be a little louder in the right ear than in the left ear. And so from those cues, you can detect the locations of sounds. You all can tell where sounds are coming from, right? Okay. But if you look in the mammalian brain, that is to say, primarily monkeys, but also humans and a few other rodent species have been looked at. There's little evidence of any circumscribed receptive fields. Okay. Instead, what we tend to see is that neurons tend to respond better to a sound located all the way over to the right, typically on the left side of the brain, or all the way over to the left, typically on the right side of the brain, and that there's a graded response pattern as sounds are located at intermediate locations. So this is basically rate coding in the horizontal dimension, and nobody knows about vertical, but in the horizontal dimension, it's basically rate coding for the angle that the sound is coming from. This rate coding of sound location is even present in neurons in the primate superior colliculus, where the neurons have both visual and auditory responses. So here's an example neuron from a study we did a while back in monkeys, showing an example of visual receptive fields. This is the neuron's response, the same neuron's response to sound. So you've got this monotonic rate-coded response to the sound location. And here are the two response curves overlaid with one another. So this immediately sounds kind of strange, right? It's two different coding formats in the same neurons. And you might then ask, well, which one is correct? If we can think of that. I mean, of course, we're at a vision conference, the visual code is correct, right? Right? How many people think the vision is correct? Okay, all right, I disagree. I think it's the auditory code that's correct. And the reason that I think the auditory code is sort of correct in this case is that this is the superior colliculus, and its job is to code for saccadic eye movements. If you electrically stimulate in the superior colliculus, you will evoke a saccadic eye movement. And the motor command to move the eyes has to be monotonically coded. You need more force to go farther, okay? And so there's thought to be a readout of the code in the superior colliculus to take that visual place map and turn it into a rate-coded horizontal component of how far to tug on the eye muscles to move the eyes. And so if you've already got the code in that rate-coded format, you don't need to perform that kind of a transformation for the auditory signals. In the interest of ending on time, I'm not going to show you exactly how we think this might actually, how to square the circle, but it turns out that you can deploy a readout algorithm that is, built for the visual code and just run the auditory signals through it and end up with more or less the right answer, because the auditory signals were already kind of okay. The other thing you get out of this is turning to the problem of coordinate transformations. So visual input is retinotopic, that is to say it's anchored to the eyes. Those auditory cues are anchored to the head. So to be able to integrate a visual scene and an auditory scene, you have to be able to put those two signals into the same coordinate transformation, coordinate system. My first paper as a graduate student was a complicated model for how to do that, drawn on the left. We now think you don't need this. Most of this model was to go back and forth between place and rate and back to place again. And if auditory signals are already kind of rate coded, if this is the sound location with respect to the head, and if you have eye movement signals that are also rate coded, because again, that's the relationship between force and position, you could simply subtract the eye signal from the sound location with respect to the head signal and get a sound location with respect to the eyes. So these are two additional examples of the way in which the coding format really kind of interplays potentially quite nicely with the kinds of computational algorithms that you might want to use to get the job done. All right, that's 7 minutes and 20 seconds, so I'm going to stop there, and we can take questions.
We have some time for a couple of questions. If anybody would like to ask a question, I invite you to line up to the microphone in this aisle here. Good.
I have one question, one comment. So is this retinotopic or spatiotopic? Because I think all your arguments work in a spatiotopic frame too. And second, perception is usually non-retinotopic and objective.
I was thinking that it's retinotopic because the kind of topological organization in V1 is retinotopic, not spatiotopic. I don't know of a similar topological area that's spatiotopic, but I would be excited to look at one if there was one.
Second, perception is usually object-based.
Yes, I think the object-based nature of perception is probably the aspect that is most poorly captured by the convolutional neural net models, and probably something that requires more attention.
I was going to comment to you, but I'm not sure how object-based it is. So I'll also comment to you. I like it. I like the particularly that you keep going back to the world, because I think that is the purpose is to understand the world rather than the 2D image. But I think you could go farther in thinking about things like redundancy, early envision, and this guy Ted Adelson, I don't know who he is, but you don't know him, maybe Phil does. Talks about the synoptic function and how important it is to compute derivatives to deal with that sort of redundancy. And just about every derivative that's interesting and important early on is something in space. And then later on, it's probably something more like tolerance and invariance, where for some of those tolerances and invariances, it becomes less clear that retinotopic is a good idea.
Great, thank you. So I take the point that algorithms that compare local values are going to be especially good for calculating derivatives and other kind of local spatial relations. Thank you. Yeah.
Thank you for the really cool talks. I was really struck by the fact that the kind of computations you need to do to survive in the world are really determine what kind of representational formats we use. In Vision, we have to integrate nearby information lots of ways because the world is spatially smooth and things like that. Whereas in the case of navigation cuts with sound and making movements, you need to make these movements in real time in simple format. It makes sense you have different codes. I'm wondering if you imagine a hypothetical organism that evolved in an environment where you needed to make like super fine grained distinctions between like the locations of sounds in the environment. And those are, you need to integrate information very locally over space. You have to do it hierarchically at multiple scales. Some sort of artificial environment where that would be the case. Do you think in that sort of situation, a retinotopic format or spatiotopic format might be more, it might evolve?
So yeah, I mean, I think one of the things I've been thinking about the difference between barn owls, where there is a spatiotopic map of auditory space, is that they in fact don't have eye movements. So they're dodging, I think, a factor that is pushing the brain to use the particular format it's using. One question we've been thinking about a lot is like, okay, a rate code is fine if you only have one signal. But if you have two things to be encoded, it's a problem. So we've been pushing on that, and we think that the answer to it might involve multiplexing different signals across time. So something like that might come into play with your kind of closer separation. in space.
Think so.
It seems worth noting that like with the polar sensitivity of neurons for auditory location, nearby locations won't ever be coded by nearby locations in place, but they will be encoded by nearby locations in some kind of state space for the two elements. So a first order convolution is not what you'd expect.
That is all the time we have for questions. Let's thank Gabe and Jenny. And I'm going to move us right along to our next session. So our next speaker is Jake Beck, who is professor and York Research Chair in the Philosophy of Visual Perception in the Department of Philosophy at York University. His talk is titled Resurrecting a Primary Secondary Quality Distinction. Take it away, Jake.
Oh, thanks so much, Chess. Thanks for having me. So Gabe gave a sort of exemplar of one sort of talk that philosophers can give, which is to look at some specific, recent trends in the sciences and sort of look at it from a bigger picture and see what we can say about it, about these big questions that interest us about the format of representation. Another thing philosophers can do, there isn't just one thing, another thing philosophers can do is look at a broad sort of historical, from a broader historical lens and try to locate where we are in time right now, our sciences compared to where they've been and maybe get a sense of where we're going. So that's what I'm going to try to do today. Could I be shorter than even Jennifer? Here we go. Okay.
Probably not.
So in the 17th century, thinkers such as Galileo, Robert Boyle of Boyle's Law fame, and John Locke drew a new distinction. And it was a distinction that proved to be just enormously influential in the history of ideas and science. And the distinction was between primary qualities like size, shape, motion, solidity, and number, and secondary qualities such as color, sound, odor, taste, and warm and cold. And the distinction that they drew had two core features. So the first is that primary qualities are objective or real in a way that secondary qualities are not. So the shape and size of an apple is really in the apple, but the color and the taste are not really in the apple. So this differed from the received view at the time, going back to Aristotle, where colors are just as much really in objects as shape is. So Locke expresses the idea of objectivity here. He writes, the particular bulk, number, figure, and motion of the parts of fire or snow are really in them whether anyone's senses perceive them or no. And therefore, they may be called real qualities because they really exist in those bodies. But light, heat, whiteness, or coldness are no more really in them than sickness or pain is in manna. So manna was a plant derivative that was used as a laxative, and it could upset your tummy. The second core feature is that ideas of primary qualities resemble objective qualities in bodies, but that ideas of secondary qualities do not. So when you see an apple, your percept, right, your idea, your mental representation resembles the shape the apple actually has, but it does not resemble the color that the apple has. And Locke expresses the idea of resemblance here. He says, the ideas of primary qualities of bodies are resemblances of them, and their patterns do really exist in the bodies themselves. But the ideas produced in us by these secondary qualities have no resemblance of them at all. There is nothing like our ideas existing in the bodies themselves. Okay, so it's hard to overemphasize how important historically this distinction between primary and secondary qualities was. It helped to lay the groundwork for the scientific revolution. So to give just one example, you find it in Newton's optics. But a lot has changed in the last 400 years. So 21st century science of the sort we've been experiencing these last few days is very different than 17th century science. So what should we make of the distinction today? Right, should we, attendees of the 2025 VSS, still think that there's an important difference between primary and secondary qualities? Or, right, is this distinction just a historical oddity, right? Not every distinction from the 17th century should be preserved, not everything they thought was correct. Descartes thought that the pineal gland was the seat of the soul. Presumably, we don't want to hold on to that. So what about this one? Well, I think that, we should still accept this distinction, but for subtly different reasons than Galileo and Boyle and Locke thought. So that's what I'm going to argue. And so for the remainder of the talk, I want to do two things. First, I'm going to argue that the traditional ways of understanding objectivity and resemblance are problematic. And then I'm going to suggest a new way of understanding them that's grounded in perception science. And that provides, I think, a viable contemporary version of the primary-secondary quality distinction. Okay, so there are multiple traditional interpretations of objectivity, but the most prominent one says that it means perceiver independent. So primary qualities do not depend on perceivers for their existence, but secondary qualities do. And it's controversial whether this was Locke's view, but it was definitely Galileo's view. So he wrote, I think that if ears, tongues, and noses were taken away, shapes and numbers and motions would remain, but not odors or tastes or sounds. Right, so if there were no more perceivers, there would still be primary qualities, but there wouldn't be any more secondary qualities. The problem is that this distinction, or this interpretation rather, relies on what is, by contemporary standards, a highly contentious view of secondary qualities. So just to give one example, many think of colors as surface reflectance properties, which exist independently of mind. So if you turn out the lights, the apple is still red because it still has the same reflectance. You just can't see its redness. So on many contemporary views of secondary qualities, they're going to be just as mind independent as the primary qualities. And that suggests that a standard 17th century interpretation of objectivity is problematic. Okay, what about resemblance? Well, we can divide resemblance into two claims. There's a positive claim and a negative claim. So the positive resemblance thesis says that ideas of primary qualities resemble objective qualities in bodies. And the negative resemblance thesis says that ideas of secondary qualities do not resemble objective qualities in bodies. And the worry that a lot of people have had is just that the positive resemblance thesis makes no sense. It's completely incoherent. And so this worry goes back to Bishop Berkeley, a contemporary and fierce critic of Locke's, who asked, how can that which is sensible be like that which is insensible? In a word, can anything be like a sensation or idea, but another sensation or idea? And his answer was that it could not be, right? An idea can only resemble another idea. Now, the Locke scholar, Michael Jacovides, brings out this difficulty with a helpful example. So a toy replica of the Statue of Liberty on the left there, right, the kind you might find in a souvenir shop. It resembles the Statue of Liberty because it has the same rough shape as the Statue of Liberty. But are we supposed to think that your idea of the Statue of Liberty has the same rough shape as the Statue of Liberty? Right, so that seems hard to accept. And so as a result, many commentators have just sided with Berkeley and just thought he got this one right and, and Locke was wrong. Jacovides is an exception. So he argues that Locke meant resemblance literally. Locke believed that your idea of the Statue of Liberty literally has the same shape as the Statue of Liberty. But his justification, Jacovidi's justification, is that given the historical context, this wasn't a crazy view for a 17th century philosopher to hold, right? Jacovidi's grants that it would be indefensible today. And by contrast, I'm going to argue that we can make sense of resemblance today, but obviously that means I need to interpret it in a different way. Okay, so the traditional ways of understanding objectivity and resemblance are problematic. But rather than giving up on the primary-secondary quality distinction, I'm going to suggest different ways of interpreting them. And I'm going to start with a new way to think about objectivity. So I think we can make sense of objectivity without mind independence. And the key is to contrast being objective with being subjective in one particular sense of that term, which has been widely abused. So some of our sciences concern subjects, organisms that sense, perceive, and act upon the world. These include, everyone's favorite subject, psychophysics, but also psychology more broadly, parts of biology. Other sciences, like physics and chemistry, are not concerned with subjects or their psychologies. They categorize and explain the world from a subject-independent perspective. Okay, so with that in mind, I want to say that a quality is objective if it features in scientific explanations that are not concerned with subjects or their psychologies. By contrast, a quality is subjective if it is not objective and features in scientific explanations of subjects or their psychologies. So subjective qualities are of interest. They're not like less scientific. They're still scientific. They're of interest, but they're only of interest because we're of interest. Subjects, us and other subjects, are of interest. Now, Locke's primary qualities are objective. Shape, size, number, motion all feature in subject-independent explanations, right? So in chemistry, we might appeal to the shape of a molecule to explain its binding properties, or we might appeal to the number of protons and electrons in an atom to explain why it constitutes a neutral oxygen atom. In astronomy, we might appeal to the size and shape of the moon and sun, along with their distance from the Earth, to explain why a solar eclipse is total. Right? These aren't going to be the most fundamental features of our objective sciences. Maybe that's 17 dimensions of strings or God knows what. But the real feature is all the same of subject-independent sciences. Now, many of Locke's secondary qualities, by contrast, are subjective. And that's true even if they're perceiver-independent. So, for example, even if you think that colors are surface reflectances, they're still going to be subjective in this sense. And one reason that secondary qualities are not objective is metamerism. So stimuli that are very different from a physical perspective are treated the same by the perceptual system. So for example, here are the very different reflectances of 4 objects that all look the same under a given illuminant. So the best we can do is identify colors with ugly disjunctions of reflectance properties. The same is going to be true of odor and taste. So for example, here are 3 different molecules that all smell minty, and then 3 more that all smell woody, and 3 more that all smell of citrus. And if you take, each of those groups of 3, right, they have nothing in common from an objective perspective. We group them together only because of the way they affect subjects, like us. Sound is not without complication, but timbre and pitch are subjective kinds. Timbre has no physical correlate that shows up in subject-independent explanations. For pitch, there is some correlation with frequency, but pitch can't be reduced to frequency, right? So pitch has a helix structure with height and chroma is periodic. Warm and cold are tricky. So if you think that we perceive temperature, then it's objective, and this would have to be a revision to Locke's list. But some philosophers, including one who's going to be giving a talk later in this session, Kathleen Akins, have argued that thermoreception is just too narcissistic to count as representing temperature. Instead, it represents how things are with your own body. And if that's right, then warm and cold might be subjective properties too. Okay. Okay, so primary qualities are thus subjective because they feature in non-subject involving sciences. Secondary qualities are subjective because they only feature in subject involving sciences. So now I want to turn to the other core feature of the distinction, which is resemblance. Okay. So remember, the worry about resemblance is just that nothing can resemble an idea except another idea. And the reply that I want to pursue is to try to tame resemblance by appeal to a structure-preserving mapping, like an isomorphism. So I'm going to first start with magnitudes, things like size, number, distance, velocity. And this will get us a lot of the primary qualities that Locke was interested in, and Galileo and Boyle, but not shape. So then I'll talk about shape after that. Okay, so the discrimination of many magnitudes, including size, distance, velocity, pressure, and number, obeys Weber's law, right? Which says that the ability to discriminate two magnitudes is a linear function of their ratio. As the ratio gets closer to 1, the ability to discriminate them deteriorates. So for example, you're better at discriminating 16 dots from 14 dots than 16 dots from 18 dots, even though the difference is the same because right, the ratio is more favorable. But you'll be just as good at discriminating 16 from 14 dots as 8 from 7 dots, or 32 from 28 dots. We can explain Weber's law with two assumptions. So the first is that external magnitudes are mirrored by internal magnitudes. So for example, as the number of dots on the screen increases, maybe the rate at which a population of neurons fires increases in a rate code. Second, we need to assume that the internal magnitudes are noisy. So for example, if we assume that the internal magnitudes increase linearly with the external magnitude and that the internal noise is scalar, then we get Weber's law. Or if we assume that the internal magnitude increases logarithmically with the external magnitude and that the noise is constant, we get Weber's law. But note that this is just the positive resemblance thesis, right? So our percepts or ideas of primary qualities mirror or resemble primary qualities themselves. As the objective magnitude increases or decreases, there's some internal magnitude in your head that increases or decreases as well. And so the internal magnitude resembles the objective magnitude. The exact shape of the resemblance is up to debate, depending on the noise that you combine with it, but there's some kind of resemblance relation. Okay, that leaves open a question, which is, what are these internal magnitudes? What is it that's resembling? One option is to understand them in neural terms, like a rate code, neural fire rate. But there is another option. So in a more Lockean spirit, we could take them to be features of conscious experience, like the felt intensity of a sensory magnitude. And I think it's important to see that these two options don't need to be viewed as conflicting, right, as mutually exclusive. So one option, for example, is just to be an identity theorist about consciousness, and then you can say that these come to the same thing. There are other options too, but okay. So I've been arguing that our representations of magnitudes, like size, number, and velocity, resemble those magnitudes. But what about shape, which is also on Locke's list of primary qualities? It turns out, right, as I'm sure you guys know, there's some fairly old evidence of a resemblance relation there too. And I'm thinking about mental rotation studies of the sort performed by Shepard and Metzler that suggests that when we use mental imagery, there's an internal vehicle that mirrors the shape itself. So the time it takes to answer whether two shapes are identical is a linear function of the degree to which they're out of rotation. Now that's imagery, not perception, but there's also evidence that imagery and perception recruit overlapping neural circuits and have the same format. And so you might think there's reason to think that the perceptual vehicles mirror external shapes. I should say a version of this argument about mental imagery and perception is defended by Ned Block in his recent book, The Border Between Seeing and Thinking. Okay, so we've explained the positive resemblance thesis in a way that differs from the literal take. But what about the negative resemblance thesis? Insofar as there's a natural mapping between secondary qualities like colors, tastes, and odors and qualities in the world, it tends to be defined over subjective kinds, right? Like ugly disjunctions of reflectances. We don't get resemblance or a natural structure-preserving mapping between our ideas of secondary qualities, our percepts of secondary qualities, and anything objective in bodies, which is what the negative resemblance thesis says. Okay, so we arrive at a distinction between primary and secondary qualities that divides things up in roughly the same way as the early modern distinction. And it respects the core features of their account, objectivity and resemblance, though it interprets them in a different, more, I think, 21st century friendly way. Who cares? Why is any of this interesting? Well, what you find interesting is largely a matter of taste, but I'll mention two reasons I find it interesting. So the first is that I think it reveals something about the history of science and the history of ideas, right? So the primary secondary quality distinction, it jump-started the scientific revolution. And I think it's fascinating to see how the distinction is still with us, but also how our understanding of that distinction has changed over time as our science has progressed. Second, I think it shows us something about perception itself, something substantive, right? It shows us that perception represents the world in two very different ways. On the one hand, it represents objective properties by mirroring them. Thinking in terms of evolution, we can imagine that in these cases, the perceptual system was sculpted by the contours of the world to the kinds that are out there when the world is carved, right, independently of us. On the other hand, the interests of the organism, right, don't always correspond cleanly to the world as it is in itself, independently of us. Sometimes it's useful to represent features of the world simply because those features matter to us. They're useful for us in some way. And in cases like this, our perceptual system latches onto subjective categories, and there is no resemblance to anything objective. We represent secondary qualities. That's all.
All right, so now we have comments from Darko Odik, who is associate professor in neuropsychology at the University of British Columbia. Take it away, Darko.
Thanks so much, Chaz. Thanks everybody else. Unlike if the previous comment could be translated to a yes and, mine is definitely going to be a no but. And so let's get going. So I'm going to make 2 points today. Both of them are going to largely focus around the resemblance criterion more so than the objectivity criterion. In some part because I think the objectivity criterion is probably right, but also because as a member of the subjective sciences, I don't get to say much for it, I think. But I do think that there are two quite serious concerns we can raise about the resemblance criterion. The first is going to be focused on whether or not Weber's law is truly the right condition for resemblance. And the second one is going to be whether the kind of multidimensional, holistic nature of conscious perception likewise causes problems for the resemblance account. So as you just heard, Weber's law is argued by Jake to be one of the important criteria for how we can establish the right kind of structure mapping. This is because an explanation of Weber's law necessitates a kind of scale that mirrors or tracks external variations in magnitude, and with the right kind of noise assumptions mirrors the kind of mistakes that humans make as well. But I want to point out that in many cases of many primary qualities, or at least seemingly primary qualities, we get widespread violations of Weber's law that would seemingly then seem to violate resemblance plus. One of the most famous examples of these is time, or perhaps better said, duration. If participants are asked to recreate a particular duration or observe two events and decide which of the two durations is longer, we straightforwardly find violations of Weber's law. So here are two examples. Weber's fraction, of course, should be constant, but time perception shows these U-shaped curves. Very low durations, usually sub-second duration, are represented with significantly more imprecision, more noise, and very long durations, more than about 3 seconds, are likewise done with not scalar noise, but super multiplicative noise. Now, notice something important here. The underlying explanation for this is that, at the level of, neuronal input detectors, we have multiple different kinds of clocks that have different kinds of noise levels, but our conscious perception of time and our ultimate time representations don't show these kinds of disjunctions. Our representations of time really do seem to have the right kind of structure mapping, but they are not following Weber's law. Another example of a problem for this account is orientation. So orientation was not discussed by Jake, but I think it quite straightforwardly meets the criteria for primary quality. Orientation is, after all, a pretty common component of, for example, theories of chemical compounds and their orientation. But orientation, too, is not going to meet Weber's law for two reasons. First of all, it is not a linear dimension. It's a circular dimension, and so mathematically, it's not going to cash out the same way. But even if we unspool this, circular dimension to try to treat it in some linear way, maybe for segments of it, we too find violations of Weber's law under that condition too, because of the well-known oblique effect, in which horizontal and vertical lines are represented with far more precision than the oblique ones. Now, ultimately, so the bad news here is that, many seemingly primary qualities violate Weber's law. And if that was the only way we could establish resemblance, that would be a problem for this account. But the good news is that I actually think Weber's law was a bit of a false flag here anyway, and that there are, in fact, more general theories of perception and decision-making and representations, including signal detection theory, that can still maintain the right kind of relationship without Weber's law. Now, the second problem, however, I think could be more significant and tricky to get out of, and this is going to be about the multidimensionality of conscious perception. So as we just heard, Jake says that resemblance can be tamed by this idea of a structure-preserving mapping, such as an isomorphism. The way that I think about that is that primary qualities can be thought about as something like one-to-one mappings, right? We have a very small list, like length representations are changed one-to-one with external changes in length. Things that are not related to length don't change those representations, whereas secondary qualities have this many-to-one relationship. Many different chemical compounds trigger the same sense of mintiness, as well as, if we're perceiving something like a color illusion, we might have a very strong representation of redness that is not coming from, the actual hue, but from the interaction between the hue and the brightness and the wavelength and this, complicated disjunction, as it was said, that leads to these weird mirroring properties that don't hold. However, I actually think that the complication here is that the primary qualities actually also show a lot of these disjunctive properties. And that in fact, we can straightforwardly demonstrate that many different perceptual magnitudes are very heavily impacted by variations of things that have nothing to do with the right kind of mirroring relationship. So we can look at it, for example, in the domain of area. If you take a look at these two objects, the diamond on the right certainly looks quite a bit larger. But of course, if we just rotate by 45 degrees, they're the same size. This is a situation where the rotation of an object changes the internal representation, the magnitude of area, without there being any actual change in the area of the object itself. We can look at other illusions as well. In this illusion, and again, thank you to Chaz who taught me about this, The straight line on the left certainly looks longer than the curved line on the right, but if we were to unspool that curved line, we would find they're the exact same length. So the curvature of an object starts to change how we perceive the length of it, even though the length is objectively the same. Now, one possible way of explaining this might be to say, look, these are all errors and malfunctions. These are all just like weirdnesses of perception and like primary qualities, just like I'm really like nitpicking. But I don't think that's actually how we should look at it. And the straightforward explanation is the one that I think most vision scientists would adopt. And that is that, we should differentiate between the level of things like input detectors that vary in response to external stimulation, the objective properties that we've been talking about, and whether that includes wavelengths of light or spatial frequency, but that perception is ultimately constructed out of these in a very important and meaningful way that allows for all kinds of interactions that are going to break the perfect mirroring relationship. In the domain of number, for example, that Jake and I both care about a lot, if we take an external stimulation like this and we simply say, okay, there's a lot of different bits of information, we're going to just focus on the 10 cat toys. We know that the input detectors that ultimately result in a number representation, they involve spatial frequency, they involve the dynamic range of the display, they involve object-based representations as well. And it is the combination of all of these that is going to yield the kind of representation that we say is a number representation. But this is exactly the same kind of thing that happens in the domain of something like color as well, where we're simply combining across hue and saturation and contrast. And so I think the uncontroversial statement here is that the perception of an object, anything, is relativized or normalized to the other features of that object. That includes area, length, duration, as I've demonstrated through some of these, but in the same way holds true for hue, bitterness, and temperature as well. So to conclude, and again, problem number 1 is about Weber's law. And again, I think that one is relatively easily solved. We can amend it. But the second one is, I think, a lot more concerning because it suggests that this idea of a mirroring relationship differentiating between primary and secondary qualities is a lot harder to sustain than we might first expect. So that's it. And yeah, thanks everybody and the organizers.
Well, we have a few notes for a question. Yes, go ahead.
Hi. I would call myself both a philosopher and a psychophysicist, and I'd like to offer some humble skepticism of sorts to the idea of objectivity, as in, I don't think you can know objective, so it's more of a metaphysical problem, not a problem for you communicator, but then there is no way to know about objective qualities or primary qualities because they are localized to specific sensory modalities. For example, when we say for motion or length, they are quite restricted to a specific modality. For example, you'd have to see something to see it moving, or you have to see something to say it's long or short. But then if you didn't have vision and you were born blind and you would just rely on auditory cues, for example, how could you possibly know about a primary quality such as length or motion? You'd have to touch it, but then if you didn't touch it, you wouldn't know. So do you see what I'm trying to get at?
Yeah, I mean, so some qualities are common sensibles. They're you can perceive them through more than one modality, and some are proper sensibles. You can only perceive them through one sensory modality. But I think the ones you mentioned, right, like motion and length, numbers, another one, are going to be common. So you can feel the length of something. Of course, if you don't feel it and you also aren't looking at it, you're not going to perceive it. But if you don't look at something, you're not going to visually perceive it. So those are all common sensibles. Those are all things that can be perceived through more than one modality.
Right. Well,
yeah.
So I think what I was trying to get is, if you don't look at something, how can you call it objective? But I think that's a different question and problem in itself.
Yeah.
Thank you.
Yeah. You do need, yeah. Okay.
I have a simple concrete question with an abstract motivation. The simple question is, it's something to be both primary and secondary quality. The abstract motivation is, I wonder if there's an assumption behind this question about, is it primary or secondary, and does it or does it not resemble? that suggests that there is one format in the visual system for these sorts of things. But another possibility, maybe more in line with like a Ramachandran vision is a bag of tricks thing, would suggest what, you know, yes, there are grid cells and place cells and everything is, there's a nice resemblance mapping there, but also we have graph theoretic representations, as in some of Bill Warren's work or something like that. We have spatial representations, we also have object representations. And in general, for some of these qualities, you can have a bunch, so that if you find a violation of resemblance in one case, that doesn't mean there's not another representation that does sustain these resemblance things. And so could things be reconciled in that way?
Yeah, I mean, I'm certainly open to the idea that there's going to be multiple formats for certain representations. Changing formats won't necessarily change whether there's resemblance. So to give one example, there's some evidence that number representations are sometimes represented in a log format and sometimes in a linear format, but there's still going to be a kind of monotonic covariation with number. And so there, in that case, there would still be a kind of resemblance. But it would, you know, so I don't think there's any a priori reason to think this couldn't happen. So we just have to look at the specific cases and see what happens. Yeah.
So this might be a little bit in the weeds, but I guess I'm kind of, as I'm listening to you go through this and in my own work, I've been trying to kind of make this connection, but with the primary and the secondary distinctions, do you find yourself at times maybe kind of coming into contact with Wittgenstein's ideas of like usage and private language, and you find that would apply here, or you think that that's really more purely a language distinction?
Yeah, I guess I hadn't made that connection. So
hit green, but once you put it there,
usually, you know, so I most of his writings, apart from some writings on color, have to do more with language and thought than with perception. So I hadn't made that connection. But if you come up with anything, I'd be interested to hear. Thanks.
first track that too.
So if I got this right, then actually all properties are secondary, because there are metameters also in space and size. And it depends on the method, in addition, distance depends on the method.
So can you give me an example of what you have in mind?
You have texture metamers, for example.
Mhm.
You get always you have the same object at different distances gives rise to the same retinal image. That's a metamer. I'm not.
Yeah.
I would like.
Yeah. Yeah.
We're basically the only sector physics.
Yeah.
But no primary ones.
Right. Yeah. So I guess we'd have to look at it. So what mattered was that the metamers were with respect to distinct objective properties, and that they were of a sort of sufficiently strong enough that there was no plausible way to identify the primary quality with some objective property that you would find in a non-subjective science. In the case of something like length or distance, I don't think that's the case. So I don't think that, I mean, some people have held this view that we don't perceive actual distance, that we perceive, or they hold this for number. You don't perceive number, you perceive numerosity. So I don't think that's very plausible. Even though there are all kinds of illusions of the sort that Darko was referring to. So I think my view can accept that there are illusions, and even that there are going to be metamers in the sense that there will be different, sort of physical realizations of the same property. But yeah, I'll stop it.
I think that's all the time we have for questions, unfortunately. But we'll be able to talk to the speaker after. Let's thank our speakers. Okay, so our final speaker is not here in person due to health reasons, but she's able to Zoom in, and it's Kathleen Akins, who is professor of philosophy at Simon Fraser University. But her commentator, Rosa Levertuzza, is here in person. And so this is going to be a hybrid presentation in many ways. We're going to have a Zoom into this room, and then a physical person in the room speaking to the Zoomer. And we think this is gonna work. So Kathleen has her slides up. And we are trying to make them full screen. And we are zooming across time zones and many thousands of miles. So Kathleen, I believe you can hear us. And if you can, now is the time to.
Sorry.
Yeah, oh great, we hear you.
I hear you. Can you hear me?
We hear you. Hello, welcome to phiVis.
Excellent, thank you. Okay. Been trying to figure out how to actually get a picture on here, but for some reason, standard things aren't working. 1 second. Here we go. There we go. Okay.
Fantastic.
Oh gosh, wrong camera. All right, we'll just, but 1 second. I just try and change the camera here.
We see you and your slides.
Yeah, I can.
You do.
Yeah, I can see that. I just don't want the FaceTime camera.
Oh, okay.
And choose video settings. 1 second. Oh, it's only showing FaceTime. Oh, that's a real pity. Okay. Watch my slides, don't watch me. Here we go.
They both look great.
All right. I really wish I could have been there. I used to attend regularly many years ago. I was hoping to reestablish that annual sojourn to the south. Okay, so today I'm going to be talking about color vision, and in particular about the puzzle of human colored vision development. Let's see. So when I'm talking about color vision, I'm not talking about the neurophysiologist's definition, but rather a color vision as we, trichromatic humans have it. We look out at the world, we see things that are colored, we see things as having colored. And so that's the primary interest that I have, and I think most philosophers and probably most vision researchers as well on human vision. So I want to start by explaining why I think there is a puzzle. And the reasons are that basically that children have a way of failing virtually all of the tests for color vision that we give them up until quite a late age. So here you have standard test, the Ishihara test. Children is asked, you see this figure down here, it's a penguin. Can you see the figure in there? And they either can or cannot. 3-year-olds, 90% of them get it correct. 100% at 5 years old. Okay, certainly older than you would think. All right. By age 2, however, children can use color as long as you don't use color names. So if you ask them the question in a tricky way, they can perform these color tests. They can do color discrimination, color matching, color categorization. They can understand function by color. So they can do all these things by 2, which shows a certain amount of sophistication, one would think, about color. Color naming, genuinely weird. Kids now learn the names of colors by about 2 years old. They know that they're color terms. They just can't use them correctly. By 3, they can use one color term. These are the eager beavers for color perception. So at 3, they can learn the color of one favorite toy. It's going to take them 1 more year to learn the next 10 names. Okay, so it gets easier, but only after a year. Farnsworth-Munsell, children are absolutely hopeless on this. No 5-year-olds can pass this test, which is a test in color ordering or seriation. So you have on one end blue tab, the other end a pink tab. Supposed to line them all up in order. 5-year-olds cannot do this. Some 7-year-olds of academics can do this. By age 11, they're basically at the same success rate as someone who's aged 70. And I have to tell you, people age 70 have really bad color vision. Okay. it was once suspected that the problem was the concept of seriation, or that maybe there wasn't enough variation between the colors. New tests were given, one a luminance test. Kids loved it. Age 5, 100% pass. Try the same one with color. They do better, but they still fail. They're consistent after 7 years. Okay. So given those kind of facts, sort of the empirical puzzle is, why is there that sort of wild stretch? After all, if you think that there are color sensations and that those appear first in vision, then surely color vision would be the very first thing that you should be able to do. So you might ask a number of different questions, why do children start to use color before they actually understand the color names? Why use before names? And then why is it so hard to learn the names if you can use the colors? Why is that first color such a big hurdle? And then why do you have trouble thereafter? And so on and so on. Okay. So that's the empirical puzzle to which we would really like answers. Second sort of puzzle is really about first-person experience, which is if you are a 2-year-old going through the acquisition of color vision, what is that like? And note that this is a question with a fair bit of irony, because if you are a neurotypical trichromat, then presumably you should know the answer to this question. All right. I'm going to talk about just 2 principles of vision because they are necessary to understanding why this is a different view about color vision. So the first principle of vision is that vision basically runs on contrast. A black sheet of paper, you don't see anything. A white sheet of paper, there's nothing to be seen. To see things in the world, that image has to have contrast, visual contrast of some kind or other. Now, there's sort of a standard mix-up, I think, or difficulty, sort of figuring out the difference between luminance and chromatic cells. Of course, the most important part is that luminance cells aren't black and white cells, and chromatic cells aren't color cells. The most basic definition is that a luminance cell compares a population with another population to have the very same spectral sensitivity. A chromatic cell compares 2 populations that have different spectral sensitivities. So an M versus an L, or an S population versus an M plus L population. Okay. The reason why they have those names is not, does not give us the definition of a luminance and chromatic cell. Rather, it's a necessary condition of being a luminance or a chromatic cell that follows directly from those 2 definitions on the last slide. A luminance cell will respond to luminance in the absence of wavelength difference, and a chromatic cell will respond to a difference in wavelength in the absence of a difference in luminance. And therein lies their name. However, that's not a sufficient condition. Those luminance cells and chromatic cells respond to all sorts of different combinations of intensity and wavelength. All right. So in the human case, sort of one of the most important facts is that coming out of the retina in the ganglion cells, which are contrast cells, there are many different kinds of ganglion cells, but the 3 main types of contrast cells divide into one luminance channel and 2 chromatic channels. I think the most important thing about this, I think from the point of view of evolution, is that each of these channels acts as a contrast filter, and it provides information that is for each of these channels that is statistically independent of the other channels. Now, with statistical independence, you get a huge range of possibilities for computation. And the other thing is that relative to all of the contrast that is in that image, that child is now at Rutgers in grad school. You don't have to feel badly for my small child. Together, those three kinds of contrast cells encode a huge whack of contrast information from any visual image. So that's where we start in vision. And then along this goes, and it becomes a major physiological division or principle within human vision. All right. Once you get your three independent sources of contrast, then you can work them. Basically, you can use them independently depending upon which one has least noise in the channel. You can use them cooperatively by combining their signals, and getting more contrast. Or you can set them up competitively and choose whichever one wins. It's a good way of sorting out which is the least noisy and which is going to give you the best information for whatever visual function it is you may be wanting to do, you being your human brain. Okay, now we can go back to human chromatic development. And we're going to do months 0 to 8 simply because I got tired after that. So at birth, a full-term, 40-week-old neonate pops out and immediately has two forms of temporal chromatic contrast. Okay, so luminance contrast and M-L, or dichromatic contrast. Okay, so standard way in which this is tested is, sorry, we go back, is this kind of screen. Okay, so a light comes on, light goes off. Does the child look at it? Yes. Okay, you can see it. When we look at the other two kinds of chromatic contrast, the child does have temporal contrast for luminance, but does not have temporal contrast for trichromatic contrast. Okay, that's not going to come online until the 4th month after birth, weirdly. Okay, what about spatial contrast? These are the two most basic kinds of contrast. Weirdly, there's no spatial contrast at birth, at least not cortically, and that's a very important thing to say. What we are testing are what we hope to be cortical vision. So 1 month after full-term pregnancy, you get spatial contrast for luminance, you get spatial contrast for dichromatic contrast, and then you have to wait another couple of months before you get trichromatic spatial contrast. Okay, so if we put this on a slide, and we'll add one more thing, you can see they're both kinds of contrast. They're temporal above, spatial below. The two types of temporal contrast that start at birth are developed unbelievably quickly. So by 3 months, you've got luminance contrast at adult levels. At 4.5 months, you've got chromatic contrast, dichromatic contrast at adult levels. And then weirdly, at 4 months, you're going to get temporal chromatic contrast just starting. This is very different than what goes on for spatial contrast. In spatial contrast, all three of these kinds of contrast just keep developing through infancy, toddlerhood, childhood, right up until about age 23, 24. There are various numbers, but it will be something like that. Okay. Right. What happens thereafter? Notice that I've left off the spatial and temporal contrast because we're going to concentrate on what happens after those two kinds of contrast come on board. And what you can see is that you start getting a whole bunch of different kinds of visual functions. And we can divide them into luminance mechanisms and to dichromatic mechanisms. Okay, now, everyone who has color vision will see that at the bottom of that slide, we have color constancy. And I'm going to come back and talk about lightness constancy and color constancy when I answer the question, why would you have those if an infant could not see the colors? Okay, so that's coming. Now, if you dig into the literature and you make sort of figure out what's been happening and at what times for infants, this is basically what you get. It's not complete. I'm sure I missed many things, but you can see that, boom, from 2 months on, you start getting quite a few chromatic functions. You also get lots of luminance functions. And it turns out that there is in this a bit of a pattern, which of course you can't discern from looking at a table. First thing that happens during, well, if you look back, just let me look back here, you kind of wonder what the heck is going on during those first 3 months. Does it really take 3 months to give you two kinds of contrast? And the answer here is that it's during this time, what is happening is that the visual system is learning the things it needs to be able to do and see in order to learn to see various properties. So in education, they talk about learning to read, and then after that, you get reading to learn, okay, learn about geography or whatever. Here, it's very much the same thing. It's seeing to learn, right? And here you have both motor and visual improvements. So you have to have convergence, divergence. You have to be able to do a nice saccade and sort of foveate on this thing, and then you have to be able to unfoveate on this thing, and so on and so forth. So there's this toolbox of mechanisms that you need in order to be able to start learning to see other properties. Okay. Now, the second thing that occurs is, and this seems quite weird given that you have an inert infant, is that you have rapid early onset of motion capacities. And given that V1 and V2 do not yet really hook up with MT yet, this capacity is underwritten by an enlargement of the pulvinar of the thalamus, its pathway to MT, and that which then serves to bypass immature V1 and V2. And in virtue of this, there are quite complex motion properties that you can see. So for example, at 7 weeks, the infant can do flow motion or global motion, and that's going to require 7 different cortical areas, visual cortical areas, plus vestibular cortex in that network. So it's actually pretty astounding, given the way the timeline looks, that infants do these. 1 second. Okay. So what I've done here is simply to highlight for you, and I'm not even sure you could read this on your screen, but to highlight for you the many forms of motion that we get within those first 8 months. And you can see that there is going to be strong motion processing using chromatic contrast information, which is unusual given the adult case. Okay. So there's motion, and of course, if you're thinking in terms of dorsal versus ventral, that's going to give you a lot of dorsal function. And I suspect what's happening here is that vision is getting ready for a mobile infant. There's lots of training of the infant because we, their caregivers, carry them around, and they move in all sorts of wonderful ways, you know, round and back and forth, and all of that. That trains up this rather complex set of motion capacities. Okay, then starting after 4 months, you start getting more object-oriented capacities, what it is that you would need in order to be able to see objects, to discern them within a scene, and so on. And it kicks off with lightness and color constancy. Okay. So here we have it. Now you can, I hope you can see, I don't know whether you can. 4 months old, you get lightness constancy and color constancy. And the question is why? Because we certainly don't see on this list anywhere the capacity to see colors. And I think the reason for this, and the reason why we have so many constancy mechanisms, both low level and high level, is that at the outset, if you have a visual system that goes about in a very complex and diverse environment, the best way to maximize contrast, and that means to maximize visibility, is to have adaptation to spectral bias. And lo and behold, children can see whether the object has changed as compared to whether the spectral bias has changed already at 4 months old. So that's very handy to have, but I suspect the real reason that infants develop it is because it's going to give you the best chance at using the contrast that is actually, as it were, in the world. Okay. So what about from the first person point of view? I'm not going to say a lot here. I think that every time you get a new mechanism for a visual capacity or visual property, you are able to see, you're able to see a specific visual property as defined by a specific form of contrast. If you are a visual mechanism and you use luminance contrast and there is no luminance contrast in the image, you don't see that property. And this is why we have this warning, which is never overinflate a nascent visual capacity. Sounded like a good beach metaphor for Florida. You have to be very careful that you know exactly what the mechanism does, because based on our own experience, we tend to add in all sorts of mechanisms that may or may not be there, such as for motion. Do we see the start of the motion? Do we see the acceleration, the deceleration, where it lands, and so on? Those are all, except for the
Sorry to interrupt you, but if you were here in person, this is the point where we would be flashing the sign saying 2 or 3 minutes remaining.
Okay,
instead,
here we
say
go.
that's it. Yes.
Okay, here we go. Sorry. Okay, so does the 9-month-old see the colors? And I suspect that they don't. And this for 3 reasons, and this is put in for the philosophers. All of the functions listed up to 9 months, they're known to require only contrast. What are made visible are these new properties that require only contrast. I think that at best, and I think this does occur, that infants are able to see a difference in properties based upon the kind of contrast that has been used, so that they know that this motion seems different from that motion, but they have no idea why. So that in consciousness, you do get a sense that there's a different mechanism, but not what it is. Okay. Now, central mystery here is, of course, so far, what exactly does a double opponent cell do? There are lots of them, and I've not said anything about what they do in color vision. And here we go. So here's what I think happens in color vision, and we are going to go over. Okay. When you're in a natural environment, the images of that natural environment are complex, they're diverse, and they involve the image itself, a number of conflations with color. Now, one thing we sort of tend to think is that, well, it's not a very difficult problem. We just kind of like pick out the best color, and that's the color of the shard leaf. But if you look at the images, you'll know that you've got all sorts of different greens at all sorts of different places. And what I don't think you do is pick out the best one. Okay. Now, as against color picking, you have an image which has no red in the image. And we know that we can see colors that are not depicted in the image in virtue of using relational processing. Okay, here are the things that I think are conflated. Let's go through them very quickly. The first one is spectral bias in color constancy. You have to be able to discount, as it were, the spectral bias of the illuminant, yellow and blue in this case. You must be able to discount texture and gloss. Texture and gloss provide us with a lot of information, but they are conflated with color. For example, there are no bright red streaks on that material, and that cat does not have its paws or arms outlined in white. Okay. Translucency. Here we've got 2 glasses of water. We have a red patch, an orange patch, and a green stripe patch. And yet it's a translucent glass with a translucent liquid. Now, it turns out that one of the first things infants do after that 4-month mark is start to figure out transparency. And yet it will take them a couple of years to do so. So here is a teacher wearing a see-through mask. And it turns out, based upon the empirical evidence, that 2-year-olds, when they are learning language, cannot see the movements of the teacher's mouth wearing that mask. It is much better to have an opaque mask for 2-year-olds learning language, which is really astounding, but speaks to exactly how difficult the problem is given a rounded, transparent surface. Okay, translucency and opacity. On the left, we know that the 2 leaves are exactly the same color of green.
I'm so
Yeah.
sorry to interrupt you again, but if you were here in person, this is the point where we'd be worried about security kicking us out of the room soon.
Okay, here we go. Okay, atmosphere. I'll just run through them. Atmosphere, motion is horrible if you look at those metal plates. And we have interreflection, we have diffuse interreflection, we have distance giving us very blue colors in the far distance. So that's all just demonstration. This is the proof of the pudding. All of these experiments show that this is the case, that all of these properties are conflated with color in the image. Now the question is, how do we go about figuring out what's the color and what's something else?
Can we let that question sit at the end of our talk? I'm just nervous that we won't get to go to our commentator and we'll lose our room.
Okay, I'm going to come to how we do these things.
Unfortunately, this has to be the end, unfortunately, but is it all right if we move to our commentator now? I'm so sorry about this.
Yep.
We won't get to get to her if we don't do that. We're going to do the talk.
Sorry.
I'm now going to introduce our commentator, and that is Rosa Lefer-Souza, who is an incoming assistant professor of psychology at the University of Wisconsin-Madison.
Kathleen, are you still with us?
I am.
Awesome. Don't worry, I saw where you were going with the end of your talk, and I'm just gonna pick it up right there. So
Okay.
nobody's gonna even miss anything. Truly, that's the part I got excited about. Trying to disentangle all those confounded properties so that we can actually arrive at a stable color percept that is meaningful and useful for behavior. So, okay. So Kathleen made a really compelling case for learning to see color, sort of bit by bit. And I always like to start any talk about color thinking about what color is for. It's just helpful for me, and hopefully it's helpful for you guys. I'll do this really quickly. What is color useful for? It's helpful for segmentation and visual search, looking for your car in a crowded parking lot. Color provides a modest benefit to object recognition, so everyone knows who this is, everybody misses him. This slide is so old now. Can you tell what he's eating? Okay, when I add color. So, for the most part, doesn't give a lot to shape, but if shape is occluded or you have similar shapes, it can be helpful. Color can tell us high-level information about the state of objects or individuals. So, tell us about ripeness or the doneness of meat or the moldiness of our bread. It can tell us about the state of a scene, whether it's dry or arid. It can tell us about the health of an individual. If there's a pallor in their face, it can tell us about the social status. Let's see, there we go. Yeah, the dominant status in this case of these baboons. And it can, whoa, did I miss it? I can't even see the slide. And it can tell us about the emotional state, the internal emotional state. So you can see beforehand, you don't know how this little guy is feeling about meeting this princess. And then you can see his cheeks are flushed and he reveals himself, his internal state. So lastly, what do we do with color? We imbue it with meaning. We use it as a symbol. We use it to communicate with each other. And so in order to do all these things, we do need for color perception to be stable, for our interpretation or representation to be stable. And I thought I would try to address Kathleen's puzzles as best I could. So color vision seems to develop slowly. Let's start there. Why does it develop slowly? Or here's a recap. We all just heard it, so I don't even need to recap it. The biggest point here that I was struck by is it actually feels relatively rapid in the beginning. By 4 months, you've got a lot of this stuff online. And then it takes until you're 4 years old to appropriately use color terms and associate them with objects. That, I think, Kathleen, you said that was genuinely weird. That felt weird to me too. But it is the case. And why then is learning to see color so slow? Well, the color signal, is really ambiguous. It's highly confounded, as Kathleen was talking about. And that means we need to go out into the world and gather a whole bunch of data. Because there are statistical regularities in the way that images are formed and out there in the environment, things like the bias of typical illuminance that we encounter. And we can, if we learn those statistics, we can exploit them to try to disambiguate the color signal and arrive at something that is stable and meaningful. So here we go. Do these cars look to be the same color or are they different? Please say something. Yay, great. Physically, of course, you've been to a meeting at the Vision Science Society before, that these are all physically the same. They're all gray when viewed in isolation. And I have just simulated these different illuminants, and your visual systems are picking up on all the cues that are available there in the image to recover the color. Now, what might it look like for color to come online bit by bit? We know that sort of the first stage, this is of course lightness constancy, but the same applies in the color domain, is just simultaneous contrast, adaptation. We heard about that. Therefore, it's unsurprising that the first development in color constancy in infants is this chromatic contrast and lightness constancy. But we know that low-level sensory mechanisms like adaptation and simultaneous contrast aren't enough to get us all the way to the finish line. Because as Kathleen was starting to get into, there are all these other properties that confound the color signal. And that means we need higher order, higher level processes to try to disentangle these things. So things like interpreting the scene, things like learning the stable canonical colors of objects that have really stable color profiles out there in the world. And let's see if we have an example. Scene interpretation. Everyone knows this picture. And of course, I have to put it up here because I'm here. In this case, the image it's the same image and put it into a ball and a cube over there, and you interpret them as being differently colored based on your interpretation of the scene structure and the lighting framework. Either it's under direct illumination or it's illuminated by shadow. Now, the reason the dress, of course, made such a big splash is that it's very rare that we struggle with this, right? Our color interpretations tend to be pretty consistent with each other and pretty stable. And maybe what infants' color experience is like before they get all of their statistics all tuned up is actually that they might see the same image and they might see it differently. Or they might see the same object under different lighting conditions and see it differently. They might make different interpretations. I'll give you one more example, of course, using the dress. This is using stored knowledge, right? So Herring first conceived this notion of maybe we can use the memory color, our knowledge about the color statistics of objects in the world to help us recover the illuminant. A longstanding cue, candidate cue was skin, and we were able to test that using the dress. So Photoshop the dress onto this lady, and I put her in Beau Lotto's cube scene, and you can see that this completely disambiguates the colors of the dress. Everybody agrees. Well, for the most part, most people agree now that the image on the left looks white and gold, and the one on the right looks blue and black. Remarkably, just putting the dress on a uniform background is not sufficient. So again, these low-level mechanisms are not sufficient to disambiguate a sort of naturalistic image like this. But here's the big test is, can we actually use skin because we have some stored representation of its color gamut? And the answer is yes, it's actually just as effective as the first image that I showed you at helping you disambiguate. I know you look at me like, it does not work for you, Jake. No, it doesn't work for everybody. You know, you're in that little bar at the bottom, and that's okay. Nothing wrong with you. In that period between 8 months and then 4 years old, what's happening with infants' color constancy mechanisms? Do they show any signs that they're starting to do scene interpretation? There's a little bit of evidence that they're starting to become sensitive to the rules about shadows. If you have an object in a scene, it should cast a shadow, and the object that is then sitting inside that shadow or outside that shadow should be dimmer or brighter, according to some basic physical principles. And sure enough, infants show signs that they're starting to be sensitive to these sorts of rules or statistics. Glossiness. Gloss is another one of these higher order color statistics, and infants around the age of, 7 to 8 months start to show signs of being sensitive to gloss. So the comparison here, they take these two objects, a green and a yellow, and they make them glossy. And when you make a yellow object glossy, you perceive it as gold. So the idea here is, do infants, they tested 5 to 6 month olds, 7 to 8 month olds, do they actually see, do they look more at the gold object than the green object, the glossy green, more so than say they look at the yellow than the green? And sure enough, they do. So it's an indicator that they're starting to be sensitive to gloss. They don't do it at 5 to 6 months, they do it at 7 to 8 months. So they're starting to become sensitive to these sorts of statistics that we know are important. Charles Darwin made these observations about his kids who couldn't use their color terms, and he deduced that they must be colorblind because they misapplied them so badly for so long. I don't know if any of you have children and have had the same kinds of concerns, but it is the case that children do name an extensive array of objects, animals, tractors, things like this, earlier than they use their color terms. And they do this in what seems to be a sort of one-shot learning kind of way. This is not the case for color. In color, it takes children longer to learn their color terms. They learn the color names at around 2 years, but then there's a solid year of pretty I don't want to say arbitrary, but difficulty applying those labels accurately to objects in the world. The thing that comes online first is they can name their favorite toy. Let's say it's Thomas the Tank Engine. They call it, you know, they figure out, okay, Thomas is blue. For a while, they might say that everything that's blue is Thomas the Tank Engine. They get pretty confused about these object color associations for quite a while. And by the time they're 5 years old, they're able to appropriately apply these labels. And I was really trying to understand and puzzle out why this would be the case, why it would take so long. And so I think what's going on is that it's actually really a challenge. So you have, color has 3 dimensions that are continuous. And the task is you need to not only assign category boundaries and carve up this space, and you know, there's lots of variability within that space. You have all your shades of green that are varying in their hue and their saturation and their lightness. And then on top of that, you have all the experience variability introduced by variations in illumination. So, you know, until you have all your mechanisms up and running and all your statistics learned, any individual that is pointing at an object and saying this is green and that is blue, if you are not experiencing stable color percepts, you may get extra confused about the application of those terms because those terms don't correspond to something that's actually stable. And there is evidence for this. So this is the end. This is in 3 to 4 year olds doing a color constancy task. And the big surprising, maybe not so surprising result is that the color constancy in 3 to 4 year olds correlates with their color naming ability. Their color naming ability and their color constancy does not correlate with age. So some kids that are younger who have better color naming ability, better color constancy. All these kids can discriminate all the colors. So, you know, I think this is sort of the answer in my mind is that, and if you have developed your color constancy, if your color constancy is more mature, your color naming is going to be more stable. And the last thing I'll say is, Kathleen, I wasn't sure exactly what you think it's like for these kids. I know that was your second puzzle to sort out, but my suspicion is that they do see color. I just think it's not very stable. And of course that makes it less useful. But I think that all of this learning is really helpful for motivating development of concepts, attaching these colors to objects and ideas, and it seems like even the development of color constancy maybe is facilitating cognitive things like language, you know, acquiring color terms, I think is actually driven by the acquisition and the maturation of color constancy mechanisms through the statistical learning. So, boom.
Thank you, Rosa. Thank you, Kathleen. We have time for 1 or 2 questions before we wrap up. So again, if you want to ask some questions, there's a mic here. We know some of you have to get to posters, so that's all right too. Jake.
Yeah, so the explanation you guys were exploring for why it's hard to, why it takes so long to name the colors and the other color abilities is because it's an intrinsically difficult task. But I'm wondering if there's another sort of explanation, which is just that color is sort of less indicative of the nature of the thing out there than, say, its shape. And so if you're just, you know, building an organism, you're going to want to make sure one of the first things it can do is recognize shape. And eventually you want to get color online, but it's not like important that color comes online at birth. It's just, you know, eventually.
For sure. Yeah, I don't disagree. And I think also shape, I think, is statistically easier to learn because of the number of features that co-occur. Like the number of features that make up a dog versus the set of features that is greenness. But yeah,
Right. Could I say something?
Absolutely.
I think that's true. Yeah, you can hear me?
Yeah, we hear you.
Okay, all right. I think that that's absolutely true. You always, in development, develop the things you need at the time that you need them or slightly before, and away you go. And so you have all of these properties that you need for getting around at the world, understanding it, interacting with it, and so on. So there is that, but there's also the fact that in order to see the colors, you need those first. So it's kind of, right, there's these two different things. One is you need everything you learned before in order to see the colors. Now, I think that it's really difficult for children because, for one, there's a huge material differences in the things, unless you're looking in a book at pictures of green, pink, and red, you are using objects, and objects have massive material differences. So for my daughter, it was a pink stuffy, it was a horrid thing, demonic. She learned the word pink, but the items she was comparing it to were a satin ribbon and a baby blanket. Okay. So if you think about the material differences between those, and particularly about a scruffy, dirty pink, right, stuffy, as compared to a glossy satin ribbon, and you see pink, those are both pink, and the kid looks at you like you're kidding. Okay, what exactly do these two things have in common? And it's simply in order to see that, they have to pull up, right, representations of these other properties, not them personally, but subpersonally, in order to figure out, right, that there is a consistency between them, namely, in the way it reflects spectral light. Okay, so it's really hard for exactly those considerations. So kids who learn their color terms by looking at books, and even pages are glossy and can make for difficulties, they're really good at books, but they can't name the colors in the world. Okay.
We have time for one last question from Ruth.
This is more of an anecdote than a question, but I really like this theory that basically color constancy is still coming online, and that's a lot of the problem. I actually had a 3-year-old living in my house for a while who, whenever the lights were red, thought all the objects were red. It was clear that color constancy was not working. But also, we got lots of samples on color naming from our older daughter, who went through a phase where every single noun had to be preceded by its color. And if there was a red thing, everything else couldn't be red. So the slightly more orange thing was orange at that point, even if they were barely discriminable, and so I think there's also this extra thing that they want to be specific. They only want to have one color name per thing. They can't have the same color. And the kids did the same thing for, like, if you had multiple kinds of shoes, they couldn't all be shoes. Like, those are shoes, and those were sandals, and those were boots. And there's like a specificity thing that kids do also, I think. That's all.
interesting.
Yeah.
Like it.
Wow.
Yay.
Okay, I think with that, we should wrap it up. People have posters to go to and talks to attend. So thank you so much for attending and sticking with us through the 5th anniversary of phiVis, and we'll see you all next year.